Hello. Whoa. Okay. Welcome to Ceph, a scalable distributed storage system for Linux, presented by Sage Weil, who designed Ceph as part of his PhD research into storage systems at the University of California in Santa Cruz. Since graduating, Ceph has continued to refine the system with the goal of providing a stable, next-generation distributed file system for Linux. Prior to his graduate work, Sage helped found New Dream Network, the company behind DreamHost and one of our sponsors. So thanks for that as well. And DreamHost now support a small team of Ceph developers. Thank you, Sage.
Thank you. Everybody hear me? All right, my name is Sage Weil. I'm going to talk about Ceph, a scalable distributed storage system for Linux. Yeah, you sort of did the introduction. So Ceph is a distributed file system, but the real question is what makes it different from other systems that are out there. First and foremost, Ceph is designed to be scalable, to grow to clusters of thousands of servers. And it's designed such that servers can be as easily added and removed from that storage cluster. So you can take a small installation of a few servers and have that sort of grow organically over time to scales of petabytes or more. The system is designed to be reliable and highly available. All data in the system is replicated across multiple nodes, and so there are no single points of failure. And furthermore, it's designed such that any individual node failure can be quickly recovered from, so you can continue doing useful work. It contains a number of advanced file system features as well, including fine granularity per directory snapshots and a recursive quota-like accounting mechanism that I'll talk about a bit later. And it also gives you access to the low-level object storage system used internally by the file system, which can be useful for specific types of applications. That also includes a lightweight distributed computation infrastructure. So sort of the design motivation behind building the system. It's largely based on shortcomings in existing systems designs. First and foremost, we want to avoid any kind of single server bottleneck and points of failure like you might have with traditional NFS type deployments. We also avoid the symmetric shared disk architecture common to most standard cluster or SAN file systems because it's difficult to scale. At a more practical level, we want to avoid any kind of manual workload partition, sort of the bane of system administrators everywhere. We all know that data sets have a tendency to grow over time and overload the servers that they're currently being stored on. And we don't want administrators spending time manually moving data from overloaded servers to less loaded servers because it's tedious and expensive to do so. And also sort of on an abstract level, we want to avoid what I call passive storage devices. Basically this idea that there are storage servers that will respond to user commands to store and retrieve data, but they aren't aware of other servers in the cluster and they certainly don't talk to them. So the sort of the structure of this talk, I'm going to cover a few key design points in Ceph and sort of discuss them in terms of their practical implications as far as using and deploying the system. And then at the end, I'll talk about the current status of the project and sort of where to go from here. First, I'm going to talk about how Ceph segregates data and metadata management. This begins with the use of an object-based storage architecture and the use of a hash-like function to specify how data is distributed across the cluster. I'll talk about the reliable distributed object storage service. That's sort of the foundation of the system. It consists of a number of intelligent storage servers that talk to each other using peer-to-peer-like protocols. And finally, I'll look at how we build a POSIX file system on top of that storage abstraction using a separate adaptive metadata server cluster. So I'll start with what I mean by object-based storage. So in contrast to traditional file systems, which sort of work with a raw disk and sort of these fixed size blocks that are sort of numbered off to some big number. Object-based storage looks at objects. They have some alphanumeric name and a data blob associated with them, sort of like a file that can range from bytes to megabytes. And they can also have named attribute pairs to sort of store metadata about that object. But in contrast to a file system, or a file rather, where files exist in a hierarchy, objects exist in a flat namespace inside one of many object pools in the storage cluster. So what we have is a cluster of servers that are responsible for storing all data objects in the system, which we call RADOS, a reliable autonomic distributed object store. So it will store some number of pools, and inside each pool are going to be a huge number of these sort of arbitrarily named objects, blobs of data. And then we have a separate metadata cluster that's responsible for creating a file system namespace, handling security and locking. And it ultimately actually stores all metadata about the hierarchy in objects in that object store. So a sort of a simple example of how this works. We can imagine a process that is running on a client host mounting the system that wants to open a file. So it opens, the process calls open foobar. The client host, in response, will send a request, an open request to the metadata server cluster. In general, the metadata server cluster should have the required metadata in its in-memory cache. That's usually what will happen. But if it doesn't, it'll send a request to the object store to load the contents of the directory foo into memory. And then assuming everything checks out, everything's okay, it'll issue a capability to the client that gives the client permission to read the contents of that file. And then when the process issues a read, the client goes directly to the object store to get the data that it needs out of the appropriate object. And then after the process closes the file, the client can relinquish that capability back to the metadata server. So there are two sort of things to notice here. First and foremost, the metadata server stays out of the I/O path. That means that the overall I/O throughput of the system can scale directly with the size of the storage cluster without having that sort of single point bottleneck. The other thing to notice is that, that's interesting, is that object locations are well known in the system. The metadata server doesn't actually tell the client which OSD to look at to find the object that it needs. It just tells it which object to look at. And the client can calculate that information on its own, which sounds a little bit strange. So how does that work? From a high level, two approaches to data placement are allocation tables, typically used by file systems, and hash functions, which are used by distributed hash tables and other distributed systems. So allocation tables have the advantage of simplicity. We just have a table full of all the objects and their locations on disk. So if you want to read some piece of data, you look it up by name in the table, you find out where it's stored, then you go to that place and you get the data that you need. Hash functions, on the other hand, work a little bit differently. Instead of looking it up, you simply calculate the location based on the name of the object, which is nice because you don't have to actually go anywhere to look up that information. When you start to scale the system, the table might be difficult to distribute across multiple nodes, although lots of systems certainly do that. Whereas the hash function sort of scales trivially. It's just an arithmetic calculation. But one of the problems with this approach is what happens when you start adding nodes to the cluster. So allocation tables are nice because it's a totally stable mapping. When you add a new storage node, every time you move an object over to the new device, you simply update the table with the new location, and that's just fine. Hash functions, on the other hand, have a tendency to sort of reshuffle everything when you start adding devices, and the number of buckets that you're hashing into changes, which is problematic when you're talking about storage because that means moving all these data objects all over the place across your network, and that's obviously not a good idea. So what most distributed systems do that use hashing, they use a technique called consistent hashing. That's designed to sort of mitigate this problem. They provide a more stable mapping so that when you add devices to the system, a smaller number of keys get remapped to new outputs. Ceph uses a similar approach, although it's a different algorithm called crush that has the same sort of idea of keeping a stable mapping, but also providing some other features for reliability. So what does data placement look like with crush? First and foremost, it's functional. You sort of give it some integer value, some derivative of the identifier of the object, and it gives you back an ordered set of devices that you can store that data on. And those, it does so such that you get a pseudo-random uniform weighted distribution across the cluster, so that all devices in the system are sort of equally utilized. And more importantly, that mapping is stable, so that when you add OSDs to the cluster, a small number of those inputs X get remapped to new outputs, which means that you don't have a lot of data migration when you start adding new devices. It does this by describing the devices in the storage hierarchy as a tree, or hierarchy that you want to align with the physical infrastructure. So for example, you might say you have lots of devices that are sort of grouped into shelves. The shelves are grouped into rack-mount cabinets, cabinets into entire rows, multiple rows in a room in a data center, something along those lines. And then you can write a rule that specifies how you want to place your data object replicas within that physical infrastructure. So you might say that I want 3 replicas of every data object. I want those objects to be stored in different cabinets so that an individual network switch failure or, say, a power circuit failure won't take out multiple copies of the same piece of data. But I might also want to say that I want all replicas to be in the same row so that the replication traffic doesn't generate lots of intra-data center network load. So what is this, how is this actually used when we start talking about the full picture of placing data in Ceph? First, the system takes file data and it stripes it over objects using some simple striping scheme. By default, we just break the file into 4 megabyte objects. Or if you're talking directly to the object store, your user application will just say, this is the object I want to store. And you would skip that step. We then take the sort of billions of objects that you might be storing and use a hash function to map them into thousands of placement groups. They're just chunks of objects that we're going to be storing. And then we use crush to take those placement groups and map them to sets of OSDs that will be responsible for storing them. The result is that we get the pseudo-random statistically uniform distribution of data across the cluster, and we get on the order of maybe 100 placement groups per node on the system. So the things to notice are that first, that this process is very fast. It's an O of log n CPU calculation to figure out where this data should be stored, where n is the size of the cluster. And there are no lookups necessary. We don't have to ask some other server where I should be putting this data. I can just calculate it. The other thing is that it's reliable. All data objects in the system are replicated multiple times. And we can also specify that those replicas are separated across these administrator-defined failure domains so that we eliminate our exposure to correlated failures. And it's also stable, so that when we add devices to the system, a relatively small number of placement groups have to be migrated to new nodes in order to restore a balanced distribution that fully utilizes our available disk space and our available network or disk I/O bandwidth. So next I'm going to look at how we build a reliable distributed object storage based on this basic strategy. So usually when people, in the old days when people said storage cluster, probably what they meant was some sort of big expensive SAN network with fiber channel disks, maybe aggregated into LUNs, or maybe you'd have a cluster file system that sort of was intelligent and knew which disks to talk to. Today, more frequently, people are looking at, or would be talking about network attached storage, where you talk to your storage devices over an IP network using something like NFS or CIFS. And typically people would be deploying disks as deploying storage in rack mount shells with bundled with the CPU, memory, NIC, RAID controller, and so forth. That's talking over a Ethernet IP type network. But in both of these cases, the servers are still passive. Individual disks or servers in the system aren't generally aware of other nodes in the system, and they don't really talk to them to do any sort of useful work. In contrast, the fundamental driving force between the Ceph storage cluster is to use this intelligent object storage daemon that handles object storage. So on each host, you have an instance of the storage daemon that is talking to a local btrfs file system using one or more disks that's responsible for actually storing that data. The daemon is going to talk over the network to any sort of clients that are interacting with the system to store and retrieve objects. But most importantly, those daemons are also going to be talking to each other so that they can actively collaborate in order to replicate data in the system, in order to consistently apply updates to all replicas of individual objects and in a safe way. They'll work together to migrate objects to their correct location in the cluster, and they'll also work together to detect node failures. And it turns out that these OSDs are able to act intelligently, specifically because everybody in the system can agree on where the data is supposed to be placed. Those daemons can work together to coordinate writes to replica peers because they know who those replica peers are. And they can work to copy or migrate objects to the correct location in the cluster because everybody can agree where that correct location is. So there's a small OSD map data structure that's used that completely specifies the data placement of all data objects in the system. That map consists of two pieces. There's information about the cluster membership, basically a list of all the OSDs that are participating in the system and their current IP address and whether or not they're up or down. And there's also a description of this crush mapping function that's used to sort of decide how those objects are going to be allocated to those devices. Where does this map come from? There is a separate cluster of monitor daemons, ceph-mon daemons, that are responsible for sort of managing all the shared centralized cluster state. So they bind to well-known addresses so that when you start talking to the system, you know who to initially talk to get authorized to actually participate in the cluster. So they keep track of cluster membership, node status. They handle authentication. They aggregate utilization statistics, so you can do things like a DF and find out how much storage you're actually using. And those clusters, or those daemons, are reliable and highly available. So they replicate all their centralized cluster state using Paxos, part-time Parliament algorithm, essentially majority voting, and they balance their load and so forth. Essentially, they're performing a function that's similar to Yahoo's Zookeeper or Google's Chubby Lock service. We're familiar with those, except that they also combine service-specific smarts instead of providing a sort of a dumb object service, storage service. So in any case, what do the OSDs actually do with this knowledge? The basic idea is that when the OSD daemon starts up, or when it detects that the map changes, it initiates a peering algorithm in which it looks at all the placement groups that it stores locally on its disk, and it talks to all the other nodes that are also responsible for storing that data. At that point, it can make sure that the placement group contents are in sync and stored in the correct location. And if they're not, it'll start some background recovery or migration process to move the data objects to the right place in the cluster. The convenient thing being that it's actually an identical process that's initiated in response to any kind of map change. So whether it's a node failure or an expansion, a cluster expansion where you're adding new storage to the system, the same algorithm kicks in and sort of moves everything to where it's supposed to be in order to give you sort of the best distribution of data. And these nodes also monitor their peers for failures. And so that if they detect that another node in the system has failed, they send a report to the monitor so it can update the OSD map so that everybody finds out about these problems. So sort of a practical example of what this actually looks like. In this example, I start up this ceph utility in watch mode. All that does is connect to the monitor and ask it to sort of feed it updates to the cluster state so you can sort of see what's happening in the system. The two things to notice here first, we see that there are 144 placement groups storing a relatively small amount of data because this is sort of a simple test cluster I just started up on my development machine. And that there are 8 OSDs. It tells us that there are 8 OSDs that are up and 8 OSDs that are in. What does that actually mean? The system considers OSD state in sort of 2 dimensions. Up-down refers to liveness, whether or not the daemon is actually running on that machine and responding on the network. And in-out refers to whether or not the crush algorithm is currently allocating data to that node in order to store it. So initially, we're using all OSDs and they're all up. I can simulate a failure by telling the system to stop OSD 0. All this actually does is just kill the daemon on the machine, or I could pull the plug, and that would accomplish sort of the same thing. And after a few moments, we see that the cluster state changes. Now there are only 7 OSDs up, and we see that that's because the monitor received failure reports from 3 other OSDs that were pairing with that machine, telling the monitor that telling the system that that OSD has failed. After a few more moments, we see the cluster state changes a few more. We see the placement group state changes, so there are now 54 placement groups that are also flagged as degraded. That simply means that not all replicas of the data that they're storing are currently online and available because that OSD is currently offline. And at this point, we can sort of wait a while, and the system will eventually decide that that OSD is actually dead and not coming back and mark it out. Or we can just do that manually. We can just tell the OSD, or tell the monitor that this OSD is gone, it's not coming back, and you should replicate that data to other nodes. And so we do that, we mark that OSD out, and then we only have 7 OSDs in the distribution. And after some time passes, we see that we end up with 10 placement groups that are active but not clean, and some number of objects that are currently degraded. That basically means that these placement groups are currently undergoing recovery. Those objects are being copied to other hosts in order to re-replicate the data so we have multiple copies of every object in the system. And as some time passes, that recovery completes. There's not very much data in this example, so it goes pretty quickly. And in the end, we get all of our placement groups again, all active and clean and online. So the system is healthy again. So how do we actually interact with these objects? The system starts by implementing sort of a basic set of operations that you can do that are sort of resemble what you would expect from a file. You can read and write ranges of the data blob associated with the object. You can set and remove attributes, and you can, of course, just delete the object entirely. But the system also allows the administrator to extend this functionality by loading dynamic object classes into the system to allow you to introduce new functionality to the cluster. So this lets you implement new methods that are based on the existing set of methods that the system provides. For example, we might use a crypto library to implement a function that will calculate the SHA-1 hash of the object data. Or we might use a JPEG library so that we can rotate a JPEG image that's stored in the object. Or maybe we'd invert a matrix or do who knows what. Sort of the sky's the limit there. The basic idea being here is that you can move the computation in the system to the data where it's stored. And you can avoid the usual read, modify, write cycles where you have to pull the data over the network, make some small change, and then write it back again. That can be expensive in terms of your network bandwidth. And the metadata server in the system actually uses this basic infrastructure internally. So directory metadata in the system is stored in objects in sort of this basic key value format. And it'll send commands to the OSD that say, just remove this one file from this directory or insert this entry here. And that avoids requiring the metadata server to read all that data in, make a small change, and write it back out And there are a number of interfaces that applications can use to interact with this basic object storage system. There's this librados library that sort of thinly wraps the internal interfaces and gives you direct parallel access to this entire object storage cluster. It gives you access to the object classes and to a simple snapshotting mechanism, which in the case of many large web applications is actually a much more convenient paradigm for storing data. They don't usually, if you're writing a big application that has its own database that keeps track of all the data in the system, for example, if you're building Flickr or something, you're already tracking all that information, and usually you're just naming files based on numbers or something like that. You don't really need that file system hierarchy to organize your data, and it's much simpler to just interact with this sort of raw storage abstraction to do that. So it has this pretty simple programming API. This is the C version here. There's also C++ bindings. You can initialize the system, open a handle to an object pool, read and write objects, call object classes. You can interact with the snapshots. And when you're done, you close your pool handle and shut down the system. There's also a command line tool that lets you do all the same things. You read and write objects, interact with snapshots. You can also get utilization information, like a DF. And we've also built this Rados gateway tool, which implements an HTTP REST interface based on the S3 storage protocol, essentially acting as a proxy so that you can have an application that is designed to talk to S3, talk to this proxy instead, and it'll then farm out the request to the backend storage system. So this is nice if you're if you want to use existing applications designed for S3, or if you simply want to hide your storage devices on a private network instead of putting them on the open big bad internet or something like that. So finally, I'm going to look at how we build a POSIX distributed file system on top of this object storage abstraction. So there's a separate metadata cluster that's responsible for building a file system hierarchy on top of this object storage substrate. It consists of some number of CMDS daemons that are participating in this dynamic cluster. Notably, these daemons require no local storage. They actually store all metadata in objects in the object store. What they do need is lots and lots of memory, because their basic purpose is to build this large in-memory cache that sort of arbitrates access to the system. And they also need a fast network so they can talk to clients interacting with the system. This cluster is dynamic, so you can easily start up new instances of the daemon, and they'll jump into the cluster and they'll get allocated load and so forth. And then later on, you can tell them to shut down, they'll redistribute their load to other nodes, and then they'll leave. So it's convenient. So how is this data actually stored? In conventional systems, we usually have an area on disk where all the file names for a directory are stored together. Each file name references some inode by number that's located somewhere else on disk in some table or in some B tree. And then an inode will then refer to some other data blocks where you can go find more directory metadata for a nested subdirectory and so forth. Ceph takes a different approach. It also groups directory content together. But what it does is embed the inode contents next to the file name that refers to it. So this gives you very good prefetching, because you can do a single object request to the store and sort of pull in the metadata for all the file names and all the inodes that they refer to in sort of one operation. And for those of you with alarm bells going off in your head, support for hard links, where you have multiple file names referring to the same file, and it still preserves for the use of an auxiliary table. It sort of helps us find just those inodes that have multiple links to them. The result is that you get very fast performance for things like find and du that have to scan this whole file system hierarchy in every single file, because they're just doing a few IOs per directory as they make their pass. The metadata servers maintain journals that they stream all updates to that part of the hierarchy to. Interestingly, these journals are allowed to go very large, hundreds of megabytes. The idea being that when we eventually do have to trim the end of the journal, and we have to update these per directory objects, we can take the cumulative effects of the operations to an individual directory over a long period of time and combine them into a single compound operation that's then sent to the OSD to make those updates to the directory. So you end up with very efficient I/O patterns for these metadata servers. And of course, the journals are also used for failure recovery. So if a node fails, then another one can come in, rescan the journal, rejoin the cluster, and also prime its cache with hot metadata at the same time. And finally, the cluster distributes the load across a number of servers using dynamic subtree partitioning. The basic idea being that you would initially have some metadata server that's responsible for handling the root directory and everything underneath it, and then it'll sort of recursively take different pieces of the hierarchy, depending on how busy they are, and farm them off to other metadata servers in sort of an arbitrary way. This approach is very scalable, because we can sort of arbitrarily partition the file system namespace across tens or even hundreds of servers. And it's also adaptive because the system is constantly monitoring load and moving busy parts of the hierarchy from busy servers to less busy servers. So you can sort of always fully utilize your available computational resources to handle all this. It'll also replicate popular metadata across multiple nodes for availability and performance. So to get a picture of what this actually looks like, in this example, we have some number of metadata servers, each represented by a different color, handling some workload. And at time 300, or just before that, we have an extreme workload shift, where all the clients sort of stop what they're doing, and they all start creating files and directories in sort of a certain part of the hierarchy that's initially handled by MDS0. After a few moments, the cluster realizes that most of the nodes are actually idle, not doing any useful work. And so it chops up that part of the hierarchy into pieces and redistributes them across the other nodes. And so we, again, are fully utilizing our available resources. A little bit later, we sort of add 2 random metadata servers to the mix, mostly just because they can, and they get assigned some work. And again, at time 450, we have another extreme shift. This time, all the clients start creating files in the same directory. And the cluster, again, notices it chops up that directory into pieces and distributes that across the cluster. And again, we're sort of utilizing all available resources. The picture for failure recovery looks sort of similar. In this case, we have 4 nodes all doing useful work. At one point, metadata server 3 fails. After 15 seconds, the system decides that unresponsive node really is dead and should be replaced. A few more seconds are spent for another node to sort of recover that journal and rejoin the cluster. And then it's back to doing useful work. We can have 2 nodes fail at the same time a little bit later. They also recover, and then the 3rd node fails and recovers. One of the nice things of using a directory subtree partitioning is that when you have a node failure, it tends to confine itself to only certain parts of the hierarchy that are affected. So the rest of the metadata servers are handling other workloads, and they can sort of continue doing useful work, even though one of them is offline. This final experiment looks at how the metadata server cluster scales. On the x-axis, we have the number of metadata servers in the cluster going all the way up to 128. And on the y-axis, we're plotting the total throughput per metadata server. So you can imagine a perfectly horizontal line in this case would be perfect linear scaling. And what we find is, of course, nothing scales perfectly. But under these workloads, we do reasonably well. For even large clusters, we're able to break up the hierarchy in lots of small pieces so that they're all doing some useful work. And this experiment is actually some 4 years old now, so the numbers probably seem a little bit small right now. But we can have up to, in the largest case, we're doing over 250,000 metadata operations per second, which at the time at least is a very large number. And if you remember that metadata operations is only talking about things like open and close and chmod, that actually corresponds to very, very high I/O rates, because you're not talking about read and write that go directly to the object storage nodes. So one of the more interesting features of the system is a recursive accounting mechanism that recursively keeps track of file, directory, and byte counts, and also modification times for all directories in the system, essentially solving sort of half of the quota problem, the accounting side, just not the enforcement. So if you look at the directory listing, one of the things you'll notice is that the file sizes are kind of big. That's because each of those values is actually a total summation over all file sizes for everything nested recursively beneath that point in the hierarchy, essentially sort of subsuming the functionality you get with DU, but without having to do a recursive scan. That means that when you're panicking because your file system is filling up and you're trying to figure out where all that space is being used at, all you have to do is do a directory listing and you can sort of see immediately where your data is stored. Yeah. No, not that I've seen at least. Usually the file directory size and things like ext3 tells you how many blocks on disk are used to store the directory metadata, but nothing really uses it. Ceph keeps the iBlocks field at 0 for the directory, so if you do a DU, you'll get the same result. It'll still add up only the files and not the directories, and you won't get this weird balloon result. You'll also see that if you look at the extended attributes, you can see a number of other numbers. You can see recursive file and directory counts. You can also see a timestamp associated with the most recent file within that piece of the hierarchy that's been modified. So things like backup programs that are scanning the system for changes can easily find out where files have been modified. So that's pretty convenient. There's also a fine-grained snapshot mechanism. Sort of the problem we're looking at is that when you start talking about a file system that's storing petabytes of data, you're going to have lots of different data sets, and you're going to have different data retention policies for those. And so doing a snapshot on the entire file system is sort of a big hammer. So instead, we designed a simple interface that lets you snapshot individual directories So there's this sort of hidden .snap directory that appears in that you can find in any directory in the system, sort of like the netapp.snapshot directory. And to create a snapshot, I just have to do a make dir, and I can call it whatever I want. So I can list that directory, and I'll see the snapshot that I just created. You'll notice that if I look in a subdirectory and list the snapshots, I can tell that that data still belongs to the same snapshot I just created, but it recursively applies to everything beneath that point in the hierarchy. It just mangles the name to keep the namespaces separate. And you have sort of the expected snapshot semantics. So if I delete a file and then look for it, it's gone. But if I look in a snapshot, it's still there. And then when I want to delete the snapshot, I just do an rmdir, and poof, it goes away. Naturally, the snapshot of data is stored efficiently. When you finally make a modification, it sort of kicks into the low-level copy-on-write mechanism in the btrfs file system that's storing these objects. So you can create these snapshots, and they're essentially free until you start modifying data. Naturally, you need some sort of file system client to actually mount this on a host and actually use it. The goal of the ceph client is to provide near POSIX semantics with strong consistency. The goal being that processes interacting on different hosts with the file system will behave the same way as those same processes operating on the same host interacting with the file system. And it does this by maintaining consistent data and metadata caches with the metadata server. The Linux client works about how do you expect. You would load the kernel module and do a mount-t ceph, the monitor IP, and you can mount it. There's also a user space implementation that you can use via the Fuse library, which means it can be used on systems where you don't have the right kernel or on other operating systems like OS X or something. There's a libceph library so that applications can directly link into the client library and call a set of POSIX-like functions. And there's also client modules implemented for the Hadoop distributed computation environment and for Hypertable database that are based on libceph that'll let those systems store data in a ceph file system. Sort of putting it all together, there are a couple different deployment possibilities. There's basically three parts of the system that you really worry about. There's the monitor daemon, the OSD, and the metadata server. So if you imagine that you have, say, 4 storage servers with a bunch of disks, you probably want to put an OSD daemon on each of them so you can use those disks to actually store useful data. You can double up the monitors since they're relatively lightweight. You just have to make sure that they're storing their sort of cluster data on a separate partition. And the metadata server is a little bit more of a problem because it doesn't use any local disk, but it uses lots of memory, so you kind of want to keep it as separate as possible. But you can deploy it this way, and it'll work fine. If you have more servers available, you probably want to separate your OSDs from your metadata servers. You probably want to put lots of disks in the OSDs and not very much, just like a boot disk on the metadata server. You could double those up with the monitors because they're pretty lightweight. Or if you have a larger cluster, you might entirely separate things out. One of the nice things is that these OSDs are actually just daemons, and so you can actually put multiple instances on a single node and point them at different disks or sets of disks. And of course, you can also just deploy all of them on a single server if you want. Just have one instance of each, and that'll work. You just won't get any of the failure tolerance and reliability that you get with the cluster, which is useful for testing or whatever. So the current status of the system, it's relatively stable, at least in a single metadata server configuration, although it's certainly not production ready. Those of you who saw Ted's talk earlier will appreciate the distinction there. The Linux client is relatively stable as well, and has been, hopefully will be merged into the mainline kernel sometime in the near future. It's been reviewed on the mailing list, and I actually sent a pull request to Linus for this last release, and he said that he wants to see more users before he pulls it in. So we're hoping that as we have more people trying the system out, that will change. It includes a Kerberos-like security infrastructure, so it can be deployed in somewhat untrusted environments. The main issue that we're seeing right now really is some interaction with btrfs that we're working on right now, improving the performance and sort of reworking the way that the journaling works so you can sort of utilize multiple disks and possibly SSDs or NVRAM to give you really low latency writes. Moving forward, future work, really what we need most is testing, and more testing. We need to stabilize the clustered metadata server and work on some disaster recovery tools so you don't have all your data eaten. We're looking at implementing a Linux block device that sort of interacts directly with the object storage layer, or possibly a storage driver for the QEMU system, so you can do VM source, sort of like the Sheepdog distributed VM storage system that you may have seen a talk on, I guess 2 days ago now. And we're also looking at alternative object replication strategies. So the object storage cluster as it stands is really designed to be deployed in a single data center where you have lots of network bandwidth and low latencies. And we'd like to see if we can make it work in a sort of a multi-data center environment where you might have more unreliable links, and you still want to get sort of low latency tolerance of failures. That's pretty much it. The license is LGPL for the user land, mainly so applications can use these libceph and libratos libraries to talk to the system directly. Current release is .18. .19 should be out in the next week or two, supporting a stable on-disk format. You can get the source code from Git, tarballs. We build Debian packages. Might be getting RPM soon. And for more information, you can talk to me while I'm here or check out the website and so forth. We're definitely interested in talking to potential users, system administrators, developers, hardware vendors, pretty much anybody interested in this sort of space as far as what you're interested in, what you want to see, that sort of thing. So with that, I guess I'll open it up to any questions.
I just want to get it clear. You're saying you can set things up so that if you lose chunks of your one of your hard drives,
storage node,
burst into flame, then you've got some failover, that sort of thing. Is that
right? So all data objects are stored on multiple nodes. So if you lose a node completely, it explodes or something, then you'll still be fine.
Right.
That's the idea.
But right now you need a pretty reliable connection between all the storage bits.
You need to be able to talk to all the storage nodes. Yeah. So I mean, one of the
but reliability is.
Yeah. So one of the goals of the sort of data distribution strategy is to sort of describe your structure in terms of your infrastructure, so that if you lose, say, a network switch that takes out a whole cabinet, you'll still be able to access other nodes in the cluster. So you can sort of minimize that risk, but there's always going to be some risk that if your router explodes or something, then you're kind of screwed no matter what.
I was wondering if you have a single storage unit, and if you're accessing it both as a file system as the object store directly, does that work, or do you have to worry about namespace issues?
Yeah, it does work. So the file system stores in like 2 or 3 different pools, object pools, and you can create as many pools as you want. And those are separate object namespaces. So you can use it that way, definitely. Yes.
Okay, in terms of the CAP theorem, have you heard of that one?
Yes.
Yep. Which of those 3 is sacrificed, and how well suited is this system for geographic distribution?
It's not particularly well suited for geographic distribution. So sort of the consistency that's sacrificed is in the name of reliability. So if you have multiple copies of your data and you lose one server, you still want to be able to make updates to it, and so we allow that. But then if you lose that copy and your old one comes back online, you're not going to have a fully consistent system because you'll suddenly have an old copy of the data and a new one. And currently when that situation comes up, the system requires you to sort of manually go in and say, I really did lose the better version and I'm just going to have to live with the old one. And so you know when that consistency is violated, but that's sort of the compromise you have to make in order to allow the system to survive.
You talked a bit about performance in IOPS, but what about throughput? Is this the sort of file system you could, for example, dump raw video onto or something like that?
Certainly, yes. Yeah, and in fact, it's probably better suited to applications where you have just huge amounts of data I/O, because you're really just most easily scaling the storage cluster where you're just like funneling huge amounts of data to all these storage nodes. Yeah.
How tightly coupled are the OSDs to btrfs?
Sorry?
How tightly coupled is it to btrfs?
Currently, it's hooking into 2 parts of btrfs. One is a transaction mechanism. So the OSD will make multiple updates on disk and sort of group those together so that they either get committed or don't in the event of a power failure. And it also hooks into the copy on write mechanism to make the snapshot stuff a little bit more efficient. That latter can be skipped if you're using HTTP or something. It'll just copy the data, just be a little bit slower. And the transactions, that requirement may go away depending on how the changes I'm working on right now with the journaling work out. So it may be possible to use this with DXT4 or something like that as well.
Is there any support for deduplication of the blocks?
Currently, no. In principle, you could do deduplication using the object store, if you were to name the object storing the data based on a hash of its contents, then you can do that sort of thing at the object storage layer. It's sort of well suited to that. But that will require all kinds of infrastructure to actually break up file content into appropriate pieces so that it all happens efficiently. So it's definitely a possible direction to go in. It's also possible that something like btrfs within the object storage node itself might do duplication, although that will never be quite as effective because you might have the same data stored on different nodes, and you won't be able to sort of reconcile that.
So carrying on the failed object storage node question, if you have one go down and it goes into degraded mode and starts replicating things somewhere else, if that one later comes back up and everything else is still cool, does it notice that it's old and then just throw everything away? Or
no. The OSDs keep a sort of a local log of all the file system, all the modifications to that placement group. And so if one goes down and then comes back up, you can very easily determine what has changed and do a very quick recovery. So if it comes back online, then it can do an efficient scan.
I had two questions. The first one was, did you implement Paxos from scratch for the ceph-mon? And
Yes.
does the MDS support renames?
Renames? Yes. So first question is yes, Paxos is implemented from scratch. With a few minor changes, it sort of has a leasing mechanism built in to sort of distribute the load efficiently. And also the metadata server does support renames. It was a pain in the butt, but it does work. So yes, the goal for the POSIX file system is to have full POSIX compliance for the most part. So all those sorts of things do work as expected. Yes, John?
I don't have a big cluster of computers. Is there some other way I could help test?
Yes, funny you should ask that. So we are going to be doing a sort of a beta testing program. So I work for DreamHost Web Hosting, and we're going to be setting up a big cluster of servers that sort of gives anybody access to it. So the idea being that we'll set up a free cluster, you can store whatever you want, and we'll try to keep it alive and sort of use that as a test case to make sure that all these recovery and scaling features work as advertised. You can either interact with it using the object storage interface or by using files. And so if you're interested, you can sign up with the promo code ceph on our website, and that'll give you a free year of hosting also. And also we can set up your account so you can access that cluster. There's also an email address, beta@ceph.newdream.net that you can email if you don't want to sign up just yet, just to find out about that. Yes?
When adding or removing storage, you danced around the fact that you have to move some data around. Is that bounded in a way that the administrator would know about? I've just added 2
You're
terabytes
talking
of
about
disk.
when you expand the storage cluster and it has to rebalance?
Right. If I've just added
Yes.
2 terabytes of disk, are you going to shift more, less, or equal to 2 terabytes of stuff?
In general, if you have 2 terabytes of disk and you add 2 more terabytes, then half that data is going to get migrated. That's sort of the ideal. In practice, you can end up with a little bit more than that because of the way that the data is distributed across the hierarchy. But if the administrator is careful about that, they can sort of throttle that migration over time and so forth. And eventually, you really do want to do that migration so that you can fully utilize all disk in the system. So it's sort of a cost you have to pay eventually. A lot of existing systems, when you add new storage, they just sit there empty. And so depending on whether all the new data gets written to the new device. So depending on whether your new data is more popular or your old data is more popular, you're always going to be sort of unequally utilizing your new and old storage. And it's very rare that actually they have a balanced distribution where you are efficiently utilizing all resource sources. So the idea is to sort of spread all that out.
Another question, is there any provision for tiers of storage in terms of access times and latency?
You can do it that way. The rule system for Crush is actually very flexible. It's actually you write statements that actually describe the steps it takes. So you might say, I want 3 replicas of data. I want my first replica to be taken from this pool of storage allocated from this part of the tree, and my second 2 replicas to be allocated on these slow SATA disks over here. Yeah, and it'll do exactly that. Yeah.
Separately. I'm not going to ask the same question again.
Okay.
If I work out my replication strategy and say, this physical RAID has got a copy of all my objects, can I snip it out as a cluster and start it up in its own cluster and use it as a cheap way to migrate data into new file systems?
Not currently, no. You could probably dream up a way to make that work, but
Well,
that's not sort of a use case.
New dream, right? You should do that.
Yeah. 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 I'd have to think about that one.
Given that you're splitting up metadata across different hosts, depending on how busy it is, do you have sort of visibility into hot directories, places that are being hit more hard than other things? Could you say this data is being accessed more, put it on more storage nodes?
Sorry, what? What was that last sentence?
Could you say this set of data is being used, is being read more, or written more, and put it on more data nodes, more storage nodes?
So the metadata does a lot of tracking internally that keeps track of how popular parts of the hierarchy are and uses that for its load balancing. So we can say internally with a lot of detail exactly what parts of the file system are being accessed. But your actual data I/O, your reads and writes, are going directly to the OSDs. And so that's sort of a little bit separate. So the way things are set up right now, there is none of that information. In principle, when the client is done with the file and it relinquishes its capability, it could feed those statistics back to the metadata server. So it could look at I/O rates as well. But that's not something that it does right now. So I guess I'd be interested in hearing what your use case is where you'd actually want to know that information to see whether it's worth doing, I guess. Yeah. Yeah.
What is the problem with geographic distribution for this area? Latency?
Yeah, it's mainly latency. So the way that the replications work right now, you send a write to the primary copy of the object, and then it replicates it to the replicas consistently, and then gives you an acknowledgement when it's completed. And the problem right now is that when you have a failure of any of those replicas, the whole process, the write, will completely block until the system decides that that node is actually dead. And what systems do that want to maintain that low latency across multiple like geographic locations is typically the client will write directly to all replicas, and when some number of them return success, then the write returns success, even if it's not all. So I might say I have 3 replicas of my data. If 2 of them reply, then my write is complete, even if this other data center is down. So you keep that low latency, even though not all replicas got updated. And then when you do your reads, then you have to sort of reconcile that. So Amazon's Dynamo system uses a strategy like that, and it introduces a lot of complexity, but it has benefits too. That's why Amazon doesn't go down when they lose an entire data center, whatever. Everything just magically works.
Okay, we're out of time. Thank you very much, Ceph and Sage. On behalf of Linux.com.au, thank you for coming to Wellington, and thank you for speaking.